Okay, we're back. We're live. We're at Think Tech Talks, and this is Monday at 1 o'clock, so it must be the SOEST show. Wish we had a little music for that. I'm going to get some music for that.
All right.
And SOEST, of course, is the School of Ocean, Earth Science, and Technology at Mānoa, which is where science lives, or one of the most important places that science lives on the campus there. And our special guests today are Professor Michael Bell, Assistant Professor of Meteorology, and Owen Shieh, who's a graduate student. Let me see if I can do this now. He's the Weather and Climate Program Coordinator at the National
Disaster Preparedness Training Center.
Preparedness Training Center. I'll see if I can do that again. You'll have to help me. So I'd like to, first of all, let's find out who you guys are and what you do, and sort of give a little bio through your perception of it. Michael, can you tell listeners who you are and what you do?
Sure. Well, like you said, my name is Michael Bell. I'm assistant professor over at the University of Hawai'i, and before that, I worked at the National Center for Atmospheric Research for about 10 years. So I was one of the people there that was in charge of deploying the National Science Foundation facilities. So radars, different temperature sensors, and in my case, I did a lot of work with aircraft. So that brought me out to Hawaii now, and I'm primarily a specialist in radar and hurricanes.
Okay, well, we need you.
All right.
We may need you bad.
I hope not.
So what's your academic training?
So I got my bachelor's degree actually from the University of Florida, and then my master's at Colorado State, and then my PhD from the Naval Postgraduate School in Monterey, California. And then I was a research professor there and a postdoc at a Naval Postgraduate School, where I taught the Navy and Air Force students about meteorology before I came here.
So you were teaching there, but you weren't actually in the Navy.
Correct. I was a civilian.
Okay.
So yeah.
It could go well either way.
Yes.
So, Monterey has some real talent over there.
Yes, it's a great place.
So on a daily basis now, with all of these titles and backgrounds and whatnot, what do you do?
Well, I teach there at the university, so I just finished teaching a course on radar meteorology, and in a couple of weeks with the new semester I'll be teaching physical meteorology, which is the study of radiation, cloud physics, and thermodynamics. And then my research is mostly on hurricanes and trying to better understand, especially intensity change. And I use aircraft data, radar data to do that type of research. So.
Okay, we're going to drill down on that in a minute. We need to know how that works.
Okay.
And you can talk about it in your vernacular, your scientific words and everything.
Okay.
Okay, and Owen Shieh, a graduate student. Tell us what you do, Owen.
So right now I'm full-time with the National Disaster Preparedness Training Center, and I'm in charge of the weather-related coursework. We're a FEMA-funded center, and we develop training courses for emergency managers, first responders around the country. So we're one of 7 national training centers for FEMA. We're part of the National Domestic Preparedness Consortium. And what we do is we fly instructors around the country and give in-person training to those who request it through their state administrative agencies in the various states. Also, the reason I came out to Hawaii in the first place, this was about 3.5 years ago, was to start my PhD program at the University of Hawai'i at SOEST. Mm-hmm. And Dr. Bell is one of the professors on my PhD committee. Mm-hmm. So
Be nice to him.
We're on the show together. So I'm still working on that in addition to my full-time work. So on the research side, what I do is also with tropical cyclones, focusing on intensity. I'm collaborating with the Joint Typhoon Warning Center, the Navy and the Air Force joint facility in Pearl Harbor, on trying to improve prediction of tropical cyclones.
That's your PhD?
My PhD research is through UH, but the project I'm trying to apply for the benefit of the Joint Typhoon Warning Center. And so they're just collaborators.
Okay, well, between you two guys, we could really figure out a lot of stuff. So let's start. What do I need all this science for? I just turn on my cell phone. It tells me what the weather's like. What else do I need?
Well,
I'm sorry I asked you that.
yeah, it's all right. Well, as you know, the forecasts that we give out are not always correct. We'll say that. It's a very complicated problem because there's the atmosphere is very complex. There's a lot of different factors that we have to take into account. So on the one hand, we have certain physical laws that we know and we understand about the atmosphere, but on the other hand, some of the processes that are involved are too small scale to simulate directly. So we have to parameterize those in our models. And so there's always kind of a balance of how much, how faithful you can be to the simulation, and also how much data you put in. So how well do we know the state of the atmosphere at any one time? And so we're working on improving the processes, the physical processes, and also the way that we initialize those models to try and basically forecast into the future. So.
Okay, well, zooming back, you know, the world, it's the earth and the water and the sky, and it's always in motion. Everything is always changing. There's energy moving hither and yon. What actually creates the weather? I mean, and weather by definition means change.
Mm-hmm.
Weather is changing forces, right, and creating something that surprises us a little bit. I mean, weather is not really that the sun is shining and it's a beautiful trade wind day. That's not weather, at least in the public perception.
Right.
We like that. We don't have to worry about that.
Yeah, right. It's the more dangerous stuff and
Yeah,
the more
yeah.
Severe weather that's really.
So what's the global, or rather, the global process of weather that like creates weather that's like negative weather?
Well, I mean, I guess the basic principle is that there's differential heating of our planet. So the sun is shining brighter here in the tropics than it is, or we get more solar radiation here in the tropics than up in the poles. And so that temperature gradient causes changes in pressure and temperature that then basically allow the weather, the air to move around. And so because of that excess energy in one place and deficit of energy in other places, that can cause these weather systems to spin up. And so in particular, the case of tropical cyclones, they need a warm ocean surface in order to form. So, and they typically need a very low, what we call vertical wind shear. So certain conditions set up right, and then that'll allow a storm to form. So if you have warm water and nice light winds, that can lead to hurricane type conditions, which is why we get them occasionally here.
Yeah, so the magic word is lead to. So if you can figure out, that these tests are being met, these conditions are existing or increasing, there's always a delta factor, right? I mean, you see how it's moving more or less or something the same.
Right.
Then you can predict on a model what's going to happen, right?
That's correct.
This is basic meteorology 101, I guess I'm talking about.
Right, and so yeah, if we know that the conditions are met, I mean, one of the challenges with a lot of times is that the conditions may be met on a fairly large scale, and it may be a fairly small scale feature that can grow into a much larger weather system. So the old adage is that if a butterfly flaps its wings in one spot, it can spin a storm up in another. Whether or not we can't model that currently, but we're doing our best to try and understand all the different scales of motion, ranging down from sort of the urban scale, so looking at flow in and around cities and tiny targeted thunderstorms, to large-scale weather systems like hurricanes or winter storms that are affecting parts of the U.S. right now.
So in the old days, I would have a barometer, which was invented in 1600 or something, and I would have a wind tester, wind vane, or whatever we call it, and I would have a thermometer, and I'm not sure what else I would have in the old days, but that doesn't help you much now.
Well, those are still a core part of our instrumentation suite, actually. So without those, we'd be in real trouble. So we need pressure, temperature, and humidity is the other big one. So we need to measure how much water vapor there is in the atmosphere. And nowadays, though, we do, one of the things that I work on is radar, and Doppler radar in particular. And so that's a lot more higher tech than some of those instruments that you mentioned.
What is Doppler as opposed to ordinary radar?
Well, an ordinary radar sends out a pulse of energy in the radio wave spectrum that bounces off the clouds, and the amount of energy that comes back to the antenna tells us how hard it's raining. A Doppler radar can actually measure the phase shift of that electromagnetic pulse. So it's very similar to the Doppler effect that you get from a siren. If there's an ambulance coming down the street, how it changes the pitch, whether it's coming towards you or away from you. So we can measure essentially that change in pitch, and that tells us how fast the wind is blowing.
Lots more information.
Yes, exactly.
Okay.
So, and then one of the new things that in Hawaii and all around the U.S. is a technology called dual polarization, where we actually send out two separate beams, one that's oriented horizontally and one that's oriented vertically, similar to the polarized glasses that you wear at the beach, correct? And so that gives us extra information on the shape of the particles, so we can tell whether they're longer or taller, and that can distinguish between ice and rain, and gives us a lot of extra
Particle
information.
being the ice and rain.
Correct. Or birds, other types of ground clutter. The radar gets signals off of all kinds of things, so it helps us separate out whether or not it's actually weather or not weather.
Maybe it's a butterfly.
It could be. Yes, exactly. So,
Okay, so but you talk as if the Doppler radar was a critical piece in meteorology these days. Is it?
I would say yes. I think it's one of our biggest advances. Really, it came of age in the 1950s and 60s, but even since then, the technological advancements with all the computers, a lot of things they had to do used to do in analog circuitry, we can now do with the digital signal processing, and so that enables us to take much better measurements than we were able to in the past. It's one of the only tools that allows us to really probe deep inside the structure of thunderstorms and hurricanes.
So I'd like to sort of bring that to the physical end of it. So you have to have a radar machine somewhere, and the radar machine, how far can it see? Hundreds of miles?
Hundreds of miles, yes.
Really?
So yes, the NexRad radars that we have 4 in the state of Hawaii. They can see up to about 400 kilometers is the maximum range. The closer you are, the better, though. You see a little bit finer resolution. So.
And you coordinate the way they point, or can they swing 360?
They swing 360, so they typically scan what we call a PPI mode, which is your old classic radar mode that, like you would see the green line going around and blinking on the scope. But then they can go up in elevation too, so they can point higher in the atmosphere and get a full volume of the whole atmosphere.
They don't go straight up, they just go up at an angle, say more than 45 degrees.
Right, the NexRad radars are limited. The radar that we just had here for research purposes, though, it can actually point straight up. So we actually use that sometimes to point vertically and look at the rain coming directly down on top of the radar.
Can we talk about that, the radar that was just the visiting radar? If I'd only known, we would have invited the visiting radar to come here on the show. But through you, we're going to talk about the visiting radar.
Sure. Well, it was called the Doppler on Wheels,
Okay.
and it was here for a project called the Hawaiian Educational Radar Opportunity, or HERO. It was a National Science Foundation sponsored project.
A wonderful acronym.
Yeah, thank you. So the National Science Foundation has a program where you can do educational deployment. So they funded the radar to come to Hawaii for 3 weeks. It was the first time it came here, and as you mentioned, it's a radar, and it's on a truck, actually. So they were able to ship it over here, and we were able to drive it around Oahu and collect measurements on the Central Valley and on the Windward Coast, and really get high-resolution, detailed measurements of the wind.
More than the radars that we have here right now.
That's correct, because the two that we have here, one is on the two closest to us. One is on Kauai and one is on Molokai, and so we're kind of halfway in between those. So we actually have overlapping coverage, but because we were able to move the radar exactly where we wanted it, we could get really high resolution, really fine scale detail of the clouds and rain that you just can't see from the regular National Weather Service radars.
Was it something that you'd love to have for your own?
Yes. 3 weeks was, we were very lucky. We had a lot of really great weather during that time, and so I think we'll need some time to digest the data that we collected, but 3 weeks is not enough. We need to, certainly like to have one here permanently.
Well, so. I mean, one on every island, did you say?
Sure. It's really just a question of resources, so yes.
So these we're going to take a break in a minute. We'll expand this conversation, but these radars deliver signals, and the signals come to some central processing unit where they are analyzed and interpreted and whatnot. And where is that, at SOEST?
Actually, for the National Weather Service radars, those are centralized through the National Weather Service. But for the Doppler on wheels, it was all self-contained in the truck. So we had 6 different monitors in there, and actually the graduate students in the department were the ones really controlling the radar, deciding where to point it, and collecting all the data on the computers right there in the truck.
They must have loved it.
They had a great time.
But it sounds like that's the thing of the future. What I mean is that you have the computers that analyze the signal right there with the radar itself, and you're not feeding it, at a distant point. Am I right?
That's correct. Well, with the advances in computing power, we're able to just do things that we've never been able to do before. So, in the old days, they actually filtered a lot of the data, so we only got a partial. Certain average quantities about the atmosphere, but now we're actually able to record a tremendous amount of more data. So we actually collected about 100 gigabytes of data an hour. When the radar was running. So we got several terabytes of data over the 3 weeks. So,
wow.
So a lot of interesting things to analyze.
Okay, so hold that thought, because we can take a short break now. But the idea is that later we're going to try to explain to the people what you do with it.
Okay.
And how you make, how you make conclusions based on this data, and what do you do with those conclusions. This is so exciting. Nobody, everybody looks at his cell phone and says, "Oh, it's going to be sunny today." We need to know much more.
Okay, great.
Okay, that's Michael Bell. We have Michael Bell, Assistant Professor of Meteorology, and Owen Shieh, he's a graduate student, both at SOEST. This is Think Tech Talks on the SOEST show. We'll take a very short break. We'll be right back.
To thank our underwriters.
Hawaiian Electric Company and its affiliates Maui Electric on Maui and Hawaii Electric Light Company on Hawaii Islands are deeply committed to the communities they serve.
Galen Ho is a senior executive of BAE Systems, a global defense, security, and aerospace company.
The High Tech Development Corporation, the state's leading technology agency, attached to the Department of Business, Economic Development, and Tourism.
Castle and COOKE, Hawaii, with a time-honored legacy that spans more than 160 years and revolves around its mission of investing in Hawaii, creating communities, and providing for the needs of our state.
Hawaii Gas, formerly the Gas Company, a proponent of the Liquefied Natural Gas Initiative, helping Hawaii achieve its transition to clean energy and a better energy future.
Collateral Analytics, a Hawaii-based tech company empowering the real estate industry with greater and faster access to the tools and data they need to make better informed property investment decisions.
I'm Nicole Hori. Thanks so much for joining us on Think Tech.
I'm Maria Kashem. See you next time.
Okay, we're back. We're live. This is Think Tech Talks on the SOEST show, the School of Ocean and Earth Science and Technology at UH Manoa. I'm Jay Fidel. We have Michael Bell, who's an assistant professor in meteorology at SOEST, UH Manoa, and Owen Shieh, who's a graduate student there and works in disaster centers, hither and yon. Tell us about your science.
So at the National Disaster Preparedness Training Center, it's actually just down the street from here. We
Downtown?
Yeah, downtown Honolulu.
Really? Mm-hmm. Maybe that's a good thing, because when the hurricanes come, we'll need your help.
So one thing we're working on is interesting. We were discussing radar earlier. So radar technology, in addition to tropical cyclone research and just researching precipitation in general, has been instrumental in helping us with tornado warning lead times around the country. And so one of our current projects at the NDPTC is developing a tornado awareness course. So I've actually just returned from several travels. Just went to Oklahoma in November to do 2 demo courses where we gathered all the emergency managers, the several fire chiefs, first responders who actually had to respond to the EF5 tornado in Moore, Oklahoma last May. We gathered them in a classroom and we demoed the course. It's a 4-hour tornado awareness course, and we're testing it in Oklahoma. Received some good feedback. And right now we're editing it, and then in January, at the end of January, we're scheduling another delivery in Atlanta. And then in March, we're looking at New York. So we want to purposely hit 3 parts of the country with different types of weather hazards, get feedback from the emergency managers, and in the next few months, hopefully reach the FEMA pilot stage, at which point, if certified, the course will be available for emergency managers to take for FEMA certification anywhere in the country.
I hope we can wait. Maybe you
It's a
have to
process,
speed it up a little bit, actually.
We're doing our best.
So, in terms of this kind of course, I mean, what is it? Video? Is it lecture? Is it combination? Is it charts and graphs? What is it?
It's a combination. It's an instructor-led training where we send 1 or 2 instructors, depending on the length of the course, to the location that's hosting, and it's in any of the 50 states and the U.S. territories. And the host agency will typically request the course through the state administrative agency, and we send the instructors. So we have a group of contracted instructors around the country, as well as those who work full-time with us here in Honolulu. And we will fly them to the location and actually host the training. For the Tornado course, it's a 4-hour course. So we're expecting about 1 instructor who will lead the course, and class of maybe 30 people. So it's interactive, it's PowerPoint based, it's also activity based. We'll do tabletop exercises and things just to help them better understand the hazard or the topic at hand.
I went to a course at the fire department. There was an organization on the mainland that was it was a private organization that taught about hydrogen fires, and the fire department didn't know anything about hydrogen fires. Do you know that hydrogen fire? You can't see it. It's invisible, which is very dangerous business. You can hear it, but you can't see it. Anyway, so they gave them a course, and it was a very good course. It was like a roadshow kind of thing, what you're describing. And I just wonder, exactly what do you teach these guys? Can you give me an example of a deliverable that you would try to, teach them?
So we have 3 different levels of courses: awareness level, performance level, and management level. We have a course, social media. It's the full name is Social Media for Natural Disaster Response and Recovery, and that's a really popular course. Lots of requests for it around the country this past year, and that's a performance level course where we actually teach the participants to use social media if they don't know already, how to create accounts, how to actually use it when it comes to managing natural hazards, natural disasters. Awareness level courses like the Tornado Awareness course is meant for a more basic level understanding of the science of the hazard, as well as what to do when the hazard threatens. And the management level would be for executives, for people who are decision makers. And so we have different levels of deliverables depending on the course topic as well as the audience.
This is really interesting. Now FEMA puts this together. You're working ultimately for FEMA? Is it federally funded through FEMA?
Yes, it's federally funded by FEMA, but we also accept some other funding sources, but primarily through FEMA. And all the course development is FEMA funded. And we're attached to the University of Hawaii, so our official name is NEPDC at the University of Hawaii. But our funding for the course development deliveries comes from FEMA.
Just a footnote, why the University of Hawaii? Why SOEST? Is it because Michael Bell is there? Why is SOEST, the University of Hawaii, so important in the FEMA program? Why?
Well, one person that was instrumental in the development of our center, we've only been around for a little over 4 years, is Dr. Carl Kim. He's a professor of urban planning at the University of Hawaii, urban and regional planning, and he's currently our executive director of our center. And so urban planning is of course very concerned with weather, climate change, a lot of those issues. And so the intersection of that naturally would overlap with emergency management and a lot of the response and even the policy side of things.
So I'm starting to get the picture. This is very multidisciplinary.
Yes, and meteorology is certainly one of those sciences that has a basic component, but also a really strong applied component, and it's a mixture of a lot of different topics.
More and more, I expect.
Yeah.
It's not like the old days. You can probably remember stories when it wasn't like this. Yeah. Well, okay, so these courses, I mean, do you stop at courses? I mean, NDPTC, the T stands for training. What happens when we have a real storm? Do you actually go out there, Owen? Do you go out there with your raincoat on and handle it? What happens?
No, so we're primarily a training center. So of course we do a lot of the work before the disaster happens. And our primary mission being training, we go around and we help with the preparedness aspect. And response and recovery typically is addressed through our training courses. The first responders of the particular location where the hazard affects is, of course, the people who will be out, boots on the ground.
Are they state and federal or just state?
The primary response will be local at first. And then, of course, the state can declare, can request assistance from the feds, at which point you have federally declared disasters.
Where's Coast Guard fit in all this, if anywhere?
Well, the Coast Guard is officially with the Department of Homeland Security, but it can also be considered a military unit. And so
They were involved in the one in New Orleans pretty heavily. I mean.
Oh yeah. So they're a federal entity.
Yeah.
And of course, you have your local first responders as well. So in the case of Oklahoma, the tornadoes, a lot of the first responders were firefighters who went out to try to survey the damage immediately as soon as the tornado passed.
Well, you get into all kinds of issues when you deal with local organizations in different parts of the country. Some of them, and I'll say it, you don't have to say it, but some of them are going to be better than others, right? Some of them are going to be very competent, others not so competent. How do you deal with that? I mean, is the course longer for those who need more training?
That's actually an excellent question. So with weather training, weather is local. That's a term that we hear a lot, right? A phrase that we hear a lot.
So is politics.
But exactly.
And I mean that with the point on it.
But weather also follows rules, natural laws, and so there's patterns. And so you actually hit the nail on the head in terms of the primary challenge that we face. Because we are a national center and we're developing courses for the nation, there are differences in terms of how different locations will implement certain ideas, and even the weather hazards will be slightly different. So the tornado awareness course, using that as an example, that's why we're piloting the courses in different parts of the country, because tornado threats in Oklahoma will be very different from those in Georgia, for example, where a lot of times the tornadoes may be obscured by heavy rain. Or threats in the Northeast, where oftentimes the tornadoes are weaker and not as long-lived. And you also have the issue of public awareness being better in one place and worse in other places. In Oklahoma, in fact, I actually had a cab driver in Oklahoma City one time tell me that supercell thunderstorms often turn right. And so these are things that
Cab drivers think of those terms.
Right, yeah. And so the technical aspect of the weather is very well, people are very well aware of that in a place like Oklahoma, where severe weather threatens every spring. On the other hand, some of the parts of the country that may be less frequented by severe weather, there's a greater challenge when it comes to raising awareness. So our primary objective is to try to help supplement what's already there by the National Weather Service in terms of weather training. They focus locally on their county warning areas, and of course we're federal. And so we're trying to fill in those gaps and to help with the awareness aspect on a national level.
You know, it strikes me, you guys are, I need some help on this, but it seems to me that this is all sort of an outgrowth of recent storms, and that Katrina had a lot to do with your program. And that Sandy in New York, also winds up your program. People get excited because, they need to have some comfort that it won't happen to them again the way it happened before. But I'm just wondering, historically, was this the way it was 10 years ago or 20? Or is this a new kind of mindset for the federal government and for the funding agencies to say, wait a minute, we can't let Katrina happen. We can't get caught short again. We have to use not only the science, but we have to use our ability to organize people and train them in order to make sure that everybody knows what to do in a crisis. It's new, isn't it, relatively?
Well, I think that the recent intense storms like Katrina that you mentioned and Sandy have really highlighted how vulnerable certain parts of our country are, and also how much economic damage that they can cause. So with that reality, we need to do something to address those issues, both from a pure research perspective to better understand, for example, where is the storm going to hit? For a tropical cyclone or hurricane, 100 miles can make a huge difference in terms of the damage at landfall, right? So, with Katrina, whether it went to New Orleans or just slightly left or right, where it was Sandy, it made a little hook at the end. And then beyond that is having the preparedness to know how to deal with that. And so I think it takes a multidisciplinary approach from the federal government to address it on all those counts. So,
and part of the multidisciplinary is exactly what Owen is talking about, is the interface between best practices, the science, and the organizations that have to get out in the field, the first responders. By the way, we're going to take a break, but I got to ask you one question. Was the cab driver right? Do the tornadoes always turn to the right? Is it true?
A lot of times in the case of supercell thunderstorms, there's a special type of thunderstorm that has a rotating updraft in the center. The tornadic part of the thunderstorm will be a right turning. So the storm will split and the favored side will be the right turning. So the local knowledge there is good enough that they're able to understand that.
Think Tech bringing you local knowledge. Okay, that's Owen Shieh and Michael Bell. Michael is assistant professor of meteorology at SOEST. That's School of Ocean, Earth Science and Technology, and Owen Shieh is a graduate student and part of I wrote this down, the NTPTC. It rolls off the tongue. My wife and I speak of little else at dinner, okay? And here we are on Think Tech Talks, the SOEST show. We'll be right back after this short break.
I'm Hong Jiang, host for Asia in Review on Tuesdays.
And I'm David Day, host for Asian Review on Thursdays. Both of us broadcast our respective shows at 4 p.m.
And my topics tend to deal with questions related to environment, culture, history, and sometimes human rights.
And my shows tend to be on international business, foreign policy, geopolitics, and national security. And you can watch our shows live on the ThinkTech website at thinktechhawaii.com.
And you can also watch us on YouTube or Olalo.
So come join us on Thursdays at 4 p.m. I'm David Day.
And on Tuesdays at 4 p.m., I'm Hong Jiang.
Aloha.
Aloha.
Okay, we're back. We're live. We're at Think Tech Talks doing the SOEST show, which is the School of Ocean, Earth Science and Technology at Mānoa, with Michael Bell, assistant professor of meteorology, and Owen Shieh, graduate student there and a part of the NTPTC, which is the National Disaster Training Center. Thank you. I got the meaning right.
Yes.
Which is very important. It's hand in glove. The science needs to execute its best practices, and it has to be, and you need the science to do the right thing. You guys are hand in glove. And you're taking a course, or you're taking a course from Michael Bell, right?
I don't think I've taken a formal course from Dr. Bell.
Maybe you should.
Well, I will. I'd like to.
Okay, well, let me go to the question of this segment of the show, and that is, what does the weather look like, Michael? I mean, where are we going on this? We know we're in climate change. We know, I know anyway, I'm morally certain that these bad storms are a function somehow. They're affected by climate change. You agree with that?
Well, I think you have to be careful. I think that climate change is definitely very real, and we have a lot of scientists who are working on the problem of this, and there are starting to come to some very strong conclusions about the projections for warming globally. Linking that to individual weather events is still very challenging because, for example, with hurricanes, we don't have a very good long record of how many hurricanes there were. Our knowledge of hurricanes, of the number of hurricanes globally, really didn't get very good until about 1970 with the advent of satellites. Prior to that, almost every hurricane that was recorded or typhoon in the Pacific was due to ship encounters. And so some of the strongest storms would not be recorded because the ships were lost. Some of the weaker storms would not be recorded because they just didn't encounter any ships. So we have to be really careful about how we link these two things. But if you think about...
Sure. Could we meet again in 6 months and have this conversation?
Sure.
See if my view changes anything?
Yes. Well, I think, though, if you start to change the statistical distribution of events, so if normally, for example, with warm waters. If you make the sea surface temperatures warmer, then that can become more favorable for hurricanes. You also change the atmospheric conditions too, though, and so we still have a lot of work to do to do that. On the other hand, as more and more people live near the coast, more and more people are living in urban centers, as those severe weather events happen, the amount of damage that's being caused is going up. So even if you can't attribute any single event to the climate change, we have more and more damage and cost of these disasters each year because of the natural growth of the human population.
So it sounds like three variables there. One is you have the traditional way, I mean, forget about climate change for a minute, of examining the weather, using the Doppler radar and all the other tools you have in your toolkit, and on the assumption that the world works pretty much the same way, now as it did last year, and there's no dramatic changes. And then you add the possibility that climate change is having an effect, and that makes it a little more complicated. Try to figure out, is it present here, and if so, how? And then you have the economic effect. So what damage can happen, and that's also a spinning ball. Mm-hmm. That's also population changes, development changes, construction. Who knows what change? They all change, and so you got a hard job. That's why my next question is going to be hard for you.
Okay.
What's the 5-year plan? And I mean, if you'd like to just limit it to the Pacific, that'd be okay.
Okay, sure. Well, I think in terms of a 5-year plan for our weather forecasting, we're really taking advantage of new computer power. So the models that we're using, for example, the National Center for Environmental Prediction just recently upgraded their computer model, and that's going to be a big impact on the success of our forecasts in the longer ranges especially. So right now, at 5 days, for example, we still don't have a lot of skill in terms of our prediction. Where we were, though, at 3 days is where a few years ago was where we're at 5 days now. So as our computers get better, as our research gets better, we're able to extend those forecasts. So I think 5 years from now, I'd say number one would be the biggest impact would be this computer power. Within 5 years, though, I think we are going to start to see more impacts of climate change throughout the world. And sea level rise is going up, and we have to deal with some of those issues. So, 5 years may not be enough to notice some of those things, but we're going to have to deal with some of those issues.
Yeah. Well, this is serious. You're going to get to be a public figure, I hope you still talk to us.
Okay.
So, right now, you have a level of confidence at 3 days that you know what's coming in. You know bad weather coming in 3 days, you can tell. I mean, I suppose before, in the way back when, you see the storm right there. So, I got a pretty high level of confidence. There's a storm which is, taking my house down the road. But now you can figure that out a few days in advance using these scientific methods.
Well, it depends on the phenomena. So, for example, big winter storms, hurricanes, we have a fairly good confidence on the track out to 3 days. The intensity, though, of a hurricane can still be, even 1 day out, we can still have some issues. Some rapidly intensifying storms, for example, Hurricane Charlie in 2004 was one that rapidly intensified before it made landfall in Florida. Owen already mentioned tornadoes. We may know that the conditions are ripe for tornadoes 2 to 3 days out, but knowing exactly where a tornado is going to go, we still only can predict that within an hour maybe, or even less than an hour. So the specific response needed really depends a lot on the phenomena. If you know that there's going to be a blizzard, for example, that's a little bit different than knowing that there's a tornado down the street. We have many different spatial and temporal scales that we have to deal with.
But it sounds, ultimately, and this must be central in your career, ultimately you have to believe that with these tools and with the analyses that you make out of the science that you will be able to get a better and better handle. So if it's 3 days now, maybe it'll be 5 days soon, maybe it'll be 10 days. Maybe there's a point where you just can't predict at all.
I think there is a limit to the predictability, and that it depends on the spatial. The smaller scale things have a much shorter timeline for predictability. Tornadoes, thunderstorms. Large scale weather, though, whether it's let's say cold fronts or hurricanes, we tend to have a little bit longer time frame. So, but for example, with hurricanes, the track is governed by large-scale features. So the main flow of the atmosphere will tell you where, kind of cork in a stream in a sense, it will tell you where the hurricane's going to blow. But the detailed processes that govern the eye wall and where the smallest scale winds are, that's something that's very challenging to predict on long time scales.
Now we here in Hawaii, which I'll focus on that for a minute, because I think SOEST is primarily focused on that rather than tornadoes. You know, hurricanes are the thing that'll really bust our chops. They'll blow up our cities, as they did in Kauai a couple times and all that. So the question is, when you're, I'm asking for your science now, when you're trying to predict a hurricane coming at the shore of Oahu, what information do you have, and how do you interpret that information to know, whether it's going to come right down Kalakaua Avenue?
Right. Well, and that's a really tough forecast. So, typical track errors are on the order of about 100 miles, even 24 to 48 hours out. So that would be a huge difference between, Oahu or Kauai, for example. So knowing specifically where the hurricane is going to make landfall is still very, very challenging. However, we have a good envelope of where we expect the storm to go. And so there's a threat level that rises associated with that. So my recommendation in general with events like that is that it's better to be prepared for the possibility that it may come right down through Waikiki, and then it doesn't. And if you have your disaster preparedness plan in place, then you're in good shape. We don't currently have the technological or the forecastability to tell you that the storm, 5 days out, the storm's going to be at your house. But we can tell you with some reasonable certainty that there's a probability of a major impact coming. And so that's one way to interpret that information.
What about the dry ice that you sprinkle on top of the clouds? Don't you do that? No.
Well, they've tried that. They've tried it, and with not so much success. There was a project called Storm Fury where they actually tried to modify hurricanes, and the results were inconclusive. We'll say that.
I mean, it didn't work. Okay, that's Michael Bell, Assistant Professor of Meteorology, and Owen Shieh, graduate student, both at SOEST, the School of Ocean. I get this Ocean, Earth Science and Technology here at Think Tech Talks. This is the SOEST show. We take one more break. We'll be right back in a minute. Aloha, I'm Jay Fidel of Think Tech. We have some news for you. In addition to our Think Tech TV show and our Asia in Review show on Olelo 54, as of January 1st, we're adding Community Matters to play also 2 hours a week. Check out thinktechhawaii.com for the specific times of each of these shows. We hope you enjoy all three. Mahalo, I'm Jay Fidel.
Aloha, I'm Maria Kashem of Think Tech Hawaii, and I want to tell you about our Think Tech talk shows. If you didn't know it, Think Tech streams video and audio for all of its shows live on the internet from 2 to 5 p.m. every weekday afternoon, and we replay them all night long on ustream.tv. Visit thinktechhawaii.com for our live stream and YouTube links. Raise your awareness on Think Tech. I'm Maria Kashem, and I'll see you there.
Okay, we're back. We're live. We're here with Michael Bell and Owen Shieh of SOEST, the School of Ocean, Earth Science and Technology at UH Mānoa, on Think Tech Talks, and we're talking about forecasting the weather at SOEST. Owen, it's really important that the community rise. Michael was suggesting too that you could have one event that would have no damage at all because it was away from a populated or developed area, and you could have another event, same exact event, which would have huge damage. So how do you deal with public reaction, evacuation? How do you deal with the possibility of big damage? Somebody's got to organize. I guess it's FEMA, huh? FEMA makes some very tough decisions in a very compressed time frame. Is that part of your course?
It is an extremely complicated situation, of course. So in recent years, FEMA came out with a statement saying, describing the paradigm of the whole community. And the whole community can take on many different meanings, but one way it can be described is that in order to properly prepare and respond to hazards, we need involvement from everybody, from not just government, but also private industry, from nonprofit, from faith-based community groups, from neighbors. So it really takes the involvement of an entire community, top down, bottom up, to properly respond to hazards.
You know what they say about meteorology? It's not about the science, it's about the relationships.
As you can say about many other things.
Yeah, right.
And so, in addition to that, in addition to the complexity of the community networking, the science and the decision making, that bridge, that connection has to be built and has to become stronger. And so as we continue, the recent disasters that we hear on the news, a lot of them are actually good examples of that bridge needing to be stronger. The meteorology in many of these cases was very good. We predicted a lot of these storms well in advance, and yet the consequences weren't avoided. A lot of the predictions were helpful in saving lives and continues to improve.
Well,
But
what's the
in
metric?
cases-
You know, what's the metric? I mean, if I tell you that a storm is coming and you do a really, really good job and you save X number of people, how can I really tell that it was, and you didn't do a good job and I save 1/2 of X number of people, how can I really judge that? Because the storm will do what the storm will do.
And unfortunately, we can't conduct a science experiment on society. Right? There's no control where you can test whether
Just do
or
the
not.
best you can. That's
You can't
all
say how many lives you actually saved with the
Yeah,
forecast.
yeah.
And so you just do your best and continue improving. I like to use Hurricane Sandy as an example of vulnerabilities in decision making, because the science of it, our computer models have improved so much that days in advance we could tell that there was a significant threat to the Northeast.
There's a lot of press about that, too.
And there was a lot of press. However, the challenge comes with the communication of the science, because technically, scientifically, a hurricane is only defined based on wind speed and whether or not the storm is considered tropical or warm core. And from the decision makers,
I need to know what the difference between.
so a typical hurricane will have, if you were to travel toward the center of the storm, hypothetically, if you were to visualize that, the temperature will become warmer. So the low pressure system is centered around a warm center.
And
on the other hand,
tropical is
that would be a tropical cyclone, right?
Okay.
And an extratropical cyclone or a mid-latitude cyclone or winter storms would include nor'easters that we hear about in the winter, the blizzards in the Northeast. Those storms are cold core. So as you get closer to the center of the storm, the temperature will be cooler. So they're governed by different physical processes. And because Sandy was approaching the territory of a hybrid storm near landfall, it was difficult to pin down what it was scientifically without confusing decision makers on the ground. And so the challenge then really, Sandy is a great example of that communication challenge, where scientifically it wasn't quite a hurricane at landfall. And because of that, because of adhering to the science, and continuing the technical definitions, we weren't able to issue hurricane warnings, technically. So instead, the National Weather Service at the time decided to issue warnings for other hazards, just separately, across the eastern seaboard. After Hurricane Sandy, of course, there was a lot of discussion about this issue.
This should be every time.
Right, because a lot of the decision makers, because it wasn't called a hurricane, underestimated the threats, particularly the storm surge.
Sounds like to me, it's a nomenclature thing. At the end of the day, it's communication. You're communicating with and that's really what your disaster preparedness is about.
Right.
And we only have a couple of minutes left, and I want to shift to you, Michael. Michael Bell, you've been in this business for a while, and you're now working with the most advanced scientific methodologies and equipment. Where is it going to go? I mean, and I'm really talking about the issue of dealing with the public. You have great science, and you're going to know a lot, but can you save us? Because ultimately meteorology is about saving us, isn't it? I mean, it's like being in the Coast Guard, you save lives.
Right. Well, I think that our job is to understand the weather and to predict what's going to happen as far out and as accurately as possible. And I think every year we've seen an increase in that. And I think where we're going in the future as we improve several things. Well, I've already mentioned the computer technology. The radar technology is getting better, so we're seeing advances in that. Satellite technology also. All that data is going into those models, and it's improving those forecasts. And I think a big part of that is the confidence in the forecasts. So if we can issue a confident forecast. So right now I mentioned, there's always going to be some uncertainty, right? We're never going to be able to get it exactly right. If we could nail it perfectly, we'd probably all be rich. But there's a certain uncertainty that we need to communicate. And so, for example, communicating that there's a low probability of a very high impact event, that's different than for example, a high probability of a low impact event, right? If the trade winds are, 15 miles an hour as opposed to 10 miles an hour, I don't think people care that much.
It's about nomenclature and communication.
Yeah. So there's some uncertainty just, from maybe whether we get a little shower over us or not. But if we have a major impact, the uncertainty in a hurricane forecast and those, if we can reduce the uncertainty and improve the confidence, I think that communication will enable then the communication to be better because people have a higher confidence in our forecasts and therefore can take action. So
there it is again. Meteorology is not about science; it's about relationships. So what are your respective duties in the event of a storm? I get up every morning and say, "Oh, nice day." Well, not today, but nice day. And I say, "Well, that makes us one day closer to the next storm." That's the way I look at it. Glass half empty kind of thing. So when that happens, do you guys have a role when we have a storm? You have to, get up early and roll out of bed and go there somewhere at 4 o'clock in the morning and do something. What do you do? Anything?
Well, since I'm not involved directly in the operations, I actually am a part of a project at the National Hurricane Center that we track the landfalling storms using radar. And so I'll be running that program. It's a program called VORTRAC that we have sent to the National Hurricane Center. And so I'll be running that program to make sure that we're monitoring the situation.
We'll be thinking of you, Michael.
Okay.
How about you, Owen? Do you have to rush off to the mainland and see what you can do?
Well, since we're not first responders, we don't put on the boots and go immediately after a storm. But while a storm is happening, of course, I'm personally watching it carefully and monitoring it and immediately trying to jot down notes and trying to see what we can do better next time around.
But are you, when you jot those notes down, do you make a call to some first responder and say, what I said, a couple of months ago? Maybe you ought to adapt a little this or that or change it or whatnot?
No, we don't keep track of people.
You want to stick by the gouge as the gouge has last been written, yeah. Well, it's really wonderful because I was in the Coast Guard, and so when I say Coast Guard saves lives, and everybody in the Coast Guard was bent on doing that. That was that's why they got in, that's why they did it. And I think there's a parallel. It's not just academic, it's that at the end of the day, the community needs you. It's a great thing.
Yeah, we're doing our best.
More and more. Michael Bell, Assistant Professor of Meteorology, and Owen Shieh, graduate student both at SOEST. And Owen is part of the NDPTC. We know about that now.
Yes.
Okay. This is Think Tech Talks, the SOEST show, the School of Ocean, Earth Science, and Technology here on Think Tech. And we've been talking about forecasting the weather at SOEST. Thank you very much, gentlemen.
Thank you.
Thank you.
Aloha.